Okay, so I know that we're talking about ecology, but your warm up was about dollars, and I swear it's relevant, but I'd like to review the warm up as a way to get to study goal number 7. You start with $100 and it grows at $10 a day. So figuring out the doubling time is pretty easy, right? You got $100, you need 100 more, that would double. And if you're getting $10 a day, how many days to reach $100? So starting with 100 plus 10 days of $10 each is 200. And like my son can do this math. Maybe I didn't explain it right. Maybe you're not in the right mindset. But my kid's in the 5th grade. He's not exactly a math genius, and this is pretty straightforward. This isn't even a math problem. My kid was trying to figure out at $1 a week allowance or whatever, how long would it take for me to buy a new fingerboard or whatever? And this math is easy. They're like paychecks. How long until you can buy a motorcycle, whatever. Um, this is an example of arithmetic growth where something grows by a regular amount, and it's really simple math. Your money in the bank just goes up in a straight line. $10, $10, $10, $10, and the math is pretty easy. And unfortunately, ecosystems aren't like that. In ecology, one of the big features of understanding change in ecosystems is that most of the growth in an ecosystem is exponential growth. Some people call this geometric growth. It's the same idea, they're just two different terms. Where things grow by a percentage, and this math is a little less simple. I have a really important math trick that shows up on every single AP test, no exception, every year, no matter what, you got to know how to do it. Um, so we did that warm up to show you um, arithmetic growth, also known as linear growth. You can see it in red on my screen here. You add the same amount every year. So it's a constant growth, and so it grows in a straight line, 10 and then 10 and then 10. The amount that's being added is always the same. You might know that this is like the line formula, y equals x plus b or whatever. And this is how a checking account grows. This part's easy. Geometric exponential growth is nonlinear. The growth is a percentage, and that means that um, growth accelerates as your values are bigger. The amount of growth gets bigger because you're using a percentage of a bigger number. So now your growth is bigger. The amount increases. The growth grows. It makes this shape called the J curve. On this screen, it's blue right now. This is like a savings account at a percentage. Maybe you've remember this problem where like some teacher in like the 7th grade or the 9th grade said you could have this checking account that grows by $1 a day and you start with $1,000,000, or you could have this checking account that grows with it starts with a penny and grows by 1% annually. And the trick is that the penny growing by 1% will eventually be much bigger than $1,000,000. Um, and that's not always easy to explain. I'm going to try. It's basically because 3% of $100 would be $3 growth, but now you've got 103. So the next time that your account grows, it's by 3% of 103, which is a little bit more than $3. And then the next time it's 3% of $106. So like the amount that's growing gets bigger at every iteration. So it changes the curve. It's called a J curve. And this is how ecosystems work. This is how populations grow. This is how invasive beetles spread through a forest. This is how COVID transmission works. right? Like you give it to 10% of the people you see. And so if there's more people who have it, then 10% of all the people that they see is bigger. And so you've seen that COVID grew exponentially in California and in the United States and most parts of the world. This is like how mold spreads in your fridge. Um, Imagine that you're trying to do the math. Like if your account's always growing by 3%, it'll grow by $3 this year. But if you have $1 million in there, 3% of $1 million is actually a whole lot of money. So that's a much bigger amount. Your growth was $3 at one point, and as your total grows, 3% of a bigger total is bigger growth. So it's a little bit of growth now, a lot of growth later. J curve. You can see this pattern in humans. It took us a few million years to reach the first billion humans, and then it took us 123 to get the second billion, and it took us 33 to get another billion, and then it took us just 14 years to get the next billion. And it kind of makes sense, right? Like if every woman has 2 kids per decade, that's not a consistent amount of babies every year, because as the population is growing, each woman having 2 kids means that the number of babies is bigger. As there's more women, there's more babies because there's more women having babies. This is percent growth. And this math is tricky. For number 7, I just want to point out that they're linear versus nonlinear. And I want to come back with a really important detail to help you do exponential growth equations. It's on every AP test. We'll be back for number 8 in a minute.